Hello and welcome to lecture 39. In last lecture we were discussing about the 3-spool configuration. Then we started discussing what all are the need of 3-spool configuration. We also have discussed about what all are the advantages of 3-spool configuration and what all are the challenges in terms of both mechanical, technical as well as commercial aspects for 3-spool configuration. So, let us move with cycle analysis for the unmixed 3-spool configuration. So, here in this case if we look at, we are having the air that will be entering from the atmosphere. This is our intake, that will be followed by fan, our IP compressor, HP compressor, combustion chamber, LP turbine, IP turbine, LP turbine. We are having say 2 nozzles. So, let us look at how our TS diagram will be looking like. So, very first component we are taking, that is our intake. So, that is what is represented by process infinity to say 2. 2 to 3, that is what is representing the pressure rise by fan. It is from P02 to P03. P03 to P04, it is representing my IP compressor stage, and 4 to 5, that is what is representing HP compressor stage. Now, 5 to 6 process, that is what is say constant pressure heat addition process in combustion chamber, and stage 6, that is what is representing the maximum turbine entry temperature. The process 6 to 7, that is representing expansion which is happening in HP turbine. Similarly, 7 to 8, that is representing the expansion process in IP turbine. 8 to 9, that is representing expansion in LP turbine. We may or may not be having tailpipe as a configuration. Here suppose say from 9 to 10, it is representing the tailpipe configuration, where we will be having drop of total pressure from P09 to P010. Okay. And from 10 to 11, that is representing core exhaust nozzle or expansion in turbine nozzle. Same way 3 to 12, it is representing expansion in fan nozzle. Okay. So, let us try to analyze this part at a component level. So, very first, as we have discussed, we are having process, that is what is say inlet process or intake process. For that intake, we will be having say diffuser efficiency or maybe total pressure loss coefficient or pressure recovery coefficient that may be given for the diffuser. So, based on that, we can calculate what will be the exit pressure from the diffuser. That is basically a function of Mach number and diffuser efficiency. The process we can assume to be adiabatic process, and that is the reason why exit temperature from the intake, it is representing as a function of Mach number. Here it says my H02 and H01, they both are same, and that is how we are able to calculate what will be the exit pressure and exit temperature from the intake. Now, let us look at the next component, that is our fan. This process we are representing as from 2 to 3. For this fan, pressure ratio is known to us. So, based on that pressure ratio, and we also have the assumption of fan efficiency at the initial stage for the cycle analysis. Based on that, we can calculate what will be the exit pressure and exit temperature. So, we can have this temperature ratio, it is a function of pressure ratio and fan efficiency. That is what will lead to give the estimation of exit pressure and exit temperature from the fan. Now, we have our next component, we can say as IP compressor. Sometimes people they are saying that as a booster compressor, and that process we are representing as say 3 to 4, and for that the pressure ratio is known to us, efficiency suppose say we are assuming for the IP compressor, and based on that, if we correlate the compression ratio, efficiency and temperature term, then we are able to calculate what will be the exit pressure and exit temperature from the IP compressor. Okay. Now, let us look at the next component, it is our HP compressor. This compression process we are representing from process 4 to 5, and for that also say compression ratio, it is known to us, efficiency as we have discussed, we can assume, we can correlate our efficiency with pressure ratio in terms of temperature, and that is what will give what will be the exit pressure and exit temperature from the HP compressor. So, basically what we are doing in cycle analysis is based on certain assumptions from previous experience or maybe from the open literature, we are assuming these numbers, and from there we start our cycle analysis. And in cycle analysis, basically we are calculating what is our, say what all are our exit pressure and exit temperatures. So, let us look at, say we have our combustion chamber, and for combustion chamber we know there may be losses, and those losses we are representing in terms of say total pressure loss. That is what will lead to give the P06 to be less than that of P05. And if I will put my say control volume, this will be the input to my combustion chamber will be m dot core into H05. At the same time we are burning the fuel, and that is the reason why we are incorporating the burner efficiency, mass flow rate of the fuel and lower calorific value. And in the exit we will be having addition of mass, approximately we can say m dot core plus m dot f, and that is what will be raising the temperature to T06. We are representing that as a H06. Let us write down the energy balance. So, input we can put this two term as input, and this is my exit term. If I will be simplifying this term, I will be able to calculate what will be the fuel air ratio for this particular engine. Okay. So, here in this case, as we discussed earlier also, maybe turbine entry temperature, that is what is known to us because of metallurgical constraints. Most of the time people they are fixing the turbine entry temperature. These days the new trend that has come, people they say like they will be having very good cooling technology, blade cooling technology, and that is what will be permitting them to move towards say higher turbine entry temperature, and their focus is more in terms of specific fuel consumption, and for that they will be fixing the value of fuel air ratio. So, suppose say that fuel air ratio is given to you, you can calculate what will be the turbine entry temperature. So, this is also one of the alternative case here. It is not that straightway this sequence you will be following. Be careful about that aspect. Now, let us look at this will be giving us the idea about what will be the fuel air ratio and what will be the exit pressure from that. Now, let us look at, suppose if I consider there is an air bleed from the HP compressor. So, if you recall in week 6 lecture 28 we have discussed about what all are the need of air bleed. So, we will not discuss here, but here you can say at some stage from the HP compressor some amount of air, that is what is being taken out, that is what we say as a air bleed. Suppose it is taken out at some temperature T04 and at some pressure say P04. Okay. Since we have taken out some amount of air, that is what I say m dot B. Okay. It is known as a bleed ratio. So, if that is the case, then the entry to my combustion chamber it will be m dot core into bracket 1 minus B at 0.5. Similarly, on other side at the exit my mass balance also will be changing. So, be careful whether the bleeding is given or not. Most of the engine, almost all engines, they are having bleed configuration these days. Okay. So, just check the data carefully. Suppose say you are planning to design say new engine, then you just ask say your aircraft manufacturing company, what is their requirement, and based on that you decide the percentage bleed. That is also one of the way. See here this course, it is a fundamental course, and that is where we are discussing about say some number we are taking as a random, but when you are doing your specific design and you are doing say specific cycle analysis for the development of engine, at that time you need to have this information with you. Okay. So, be careful what is a number or what number you want to select with. So, if I will be putting my energy balance in this case, then my equation, that is what will be changing here. So, let me put this in overall sense. It says my fuel air ratio, be careful, this fuel air ratio is m dot f divided by m dot core, because we are interested in what is going inside my core engine. That is what is given by 1 minus b H06 minus H05 divided by this efficiency into calorific value minus H06. Okay. Now, let us move towards the next component. The next component what we have is our HP turbine, and since we have taken the bleed, so let us look at what is the purpose of HP turbine. We know this HP turbine, it is used to rotate my HP compressor. So, let me put the work balance here. It says my HP work done, that is what is equal to what work, that is what is required by the compressor. And here we are introducing the term, that is what is called say mechanical efficiency. Now, in terms of my work equation, that is what is mCp delta T0. Be careful what mass flow rate, that is what is entering inside my HP turbine. It is 1 plus F minus B into m dot core. Do not commit mistake here. Same way for HP compressor, what we have done, say some amount of air, that is what is going inside. So, that is what I say m dot core Cp delta T0. So, at some location say 4B, we are extracting some amount of air, that is the reason why it is T04B minus T04. Now, in later stages 1 minus B amount of air, that is going in the later stages, that is why it is say m dot core 1 minus B Cp T05 minus T04B. Do not get confused here, just look at the figure carefully and try to write down the equation. It is preferred you just take pen and paper and try to write down this equation, so you will not commit any mistake. Now, let me put this as a balance, because our requirement is to calculate what will be the exit temperature from the HP turbine. Similarly, we have information about the isentropic efficiency of the turbine. This efficiency we are correlating in terms of expansion ratio, or we can say pressure ratio, that is what will be giving the number for say what will be the exit pressure from this HP turbine. So, we will be calculating what will be the exit pressure and exit temperature from the HP turbine. Now, let us move towards the next component. What we have is our IP turbine. This IP turbine what we have, that is what is used to rotate our IP compressor. Okay. So, we will be writing down the work balance. Just try to write down the equation. Let us see, are you able to write down the equation? What it says here, my work will be m Cp delta T0. What will be m here? Okay. So, let us look at what is m here. Here in this case, this m will be m dot core into 1 plus F minus B Cp into delta T0 is T07 minus T08. At the same time, for HP for IP compressor, this equation will be m dot core Cp T04 minus T03. Okay. We are not doing any bleeding from IP compressor, that is the reason why we will not be having any change in terms of mass flow rate. Be careful about this. So, once we have all this information, we can calculate what will be the exit temperature from our IP turbine. And for IP turbine also, we can assume the number based on past experience or based on say open literature at the initial stage, From that we can correlate this efficiency in terms of say pressure ratio, or we can say expansion ratio, and that is what will lead to give the exit pressure and temperature from the IP turbine. Okay. Now, the next component we have is our LP turbine. This LP turbine is mainly being used to rotate only the fan. Can you write down the equation for the work balance? Okay. So, here I say my LP turbine work, it is m dot into Cp delta T0. What will be the m dot here? This m dot will be m dot core into 1 plus F minus B Cp delta T0. At the same time, the mass, that is what is entering inside my fan, that is what is m dot core into 1 plus beta Cp T03 minus T02. Be careful about this formulation. This is coming similar to what all we have discussed for turbofan engine. So, you should not commit mistake here. So, if that is the case, you can calculate what will be the exit temperature from the LP turbine. Based on what will be the isentropic efficiency, we can calculate what will be the exit pressure and exit temperature from the LP turbine. Okay. So, you can easily solve this numerical in this sense. Now, let us move towards the next component we have is say tailpipe, or people they used to say jet pipe. That is basically before exiting the gas towards the nozzle, it has been connected with the constant area duct, and for this constant area duct it will be having some losses because of friction, and that is what will lead to reduce the pressure at the exit of the tailpipe or at the entry of the nozzle. And at the same time we can consider the flow process to be adiabatic process, that is the reason temperature remains constant. So, let us put that as a term. So, we will be able to calculate what will be the exit pressure and exit temperature from the tailpipe. Now, very important component we have is our nozzle. For nozzle, the logic, that is what will be remain similar to what all we have discussed up till now. What we will do? We will be first calculating what will be the critical pressure ratio. So, here we are having two nozzles, one it is my turbine nozzle, second that is what is my fan nozzle. So, for both the cases we will be calculating our critical pressure, and based on that critical pressure we will be comparing this pressure with the atmospheric pressure, and we will be deciding whether our nozzle is choke nozzle or unchoke nozzle. Under the choke nozzle condition, the exit pressure we need to assume or we need to select. Under unchoke condition also we need to select our exit pressure. So, let us look at how do we do the calculation. Suppose if I consider say very first turbine nozzle. So, my critical pressure ratio is P010 over Pc, that is what is the function of turbine, say it is the function of nozzle efficiency and specific heat ratio. Suppose if I consider my critical pressure, that is what will be coming as less than say P infinity or the atmospheric condition, then we can say my exit pressure, that is what will be say equal to my atmospheric pressure. That condition we say as a unchoke condition. We will be calculating what will be the exit temperature from the nozzle, then we will be calculating what will be the exit velocity from this nozzle. Similarly, suppose if I consider say we have our nozzle, it is choke condition where my critical pressure it is greater than that of my atmospheric pressure, then my exit pressure will be equal to critical pressure. We can calculate what will be my temperature ratio, and based on that temperature ratio we can calculate what is our static temperature at the exit of the nozzle, and from where we will be calculating our exit velocity. Now, let us look at say next we have our fan nozzle. For this fan nozzle we will be calculating our critical pressure ratio. Here be careful, this nozzle efficiency is for the fan and the specific heat ratio it is for the air. Okay. So, this specific heat ratio it is say around 1.4. Again we will be checking with whether our nozzle is chalk or unchoke. Suppose if I consider say unchoke condition, we will be having our exit pressure as atmospheric pressure. We can calculate the static temperature, and based on that static temperature we will try to calculate the exhaust velocity. In case of chalk nozzle, my critical pressure will be greater than that of atmospheric pressure. So, the exit pressure will be equal to my critical pressure. Based on this equation, we can calculate what will be the exit static temperature, and from this exit static temperature we can calculate what will be our velocity. Okay. So, once we have all these components known to us, we will be reaching to the calculation of velocities. We know once we have this velocity term, it is known to us, we are able to calculate what will be the performance parameters. So, these performance parameters we are writing in terms of very first equation is for thrust. This thrust we are writing in terms of cold thrust as well as the hot thrust. Suppose if I consider this is the equation where we are not having any air bleed, but suppose if we are having the bleed, then in the case of my hot section, my mass flow equation, that is what will be changing. So, be careful about this formulation. Same way thrust specific fuel consumption we are writing in terms of m dot f divided by thrust. This m dot f is nothing but it is the fuel air ratio into m dot core. The important parameter for this high bypass ratio engine or any bypass ratio engine is to calculate the propulsive efficiency. This propulsive efficiency we can say in terms of V infinity into T. This T we are writing as Th plus Tc, and here this is what is my exhaust losses. So, that is what we are writing. Suppose say if we are having say bleeding, then this formulation will be coming as 1 plus f minus b, and this is my velocity term. Similarly, this is representing the losses in fan. And once we have this, suppose if we are having say bypass ratio known, we can use this correlation also. Next component of our interest is the thermal efficiency. That is what will be having denominator as m dot into Cv. Okay. So, once we have our propulsive efficiency and thermal efficiency, we can move with the calculation of overall efficiency, and this overall efficiency we are writing as say thermal efficiency into propulsive efficiency. Sometimes we used to say as thermopropulsive efficiency. Now, once we have all this information, you can do the calculation. This calculation we can do at ground condition, we can do this calculation at cruise condition. Maybe if you are smart enough, you can make a program, and according to that program you need to put the logics. Logic basically will be in terms of what will be the nozzle condition, whether it is chalk or unchoke, and based on that logic it will be calculating the velocity components, and you can do your plotting for say effect of various parameters on this performance parameters. Now, let us take one numerical here. Maybe you just try to solve this numerical. In next lecture we will give the solution for this. So, it says we are having 3-spool turbofan engine at its preliminary design stage, and this is at flight condition, it is 11,000 meter, flying Mach number is 0.83. At that 11,000 meter, temperature is 216.65 Kelvin and pressure is 22.63 kilopascal. Fan pressure ratio is 1.5, IPC pressure ratio is 5.2, HPC pressure ratio is 4.8. Consider bypass ratio of the engine to be 8.5. Turbine entry temperature you can select say 1800 Kelvin. It says the total pressure loss in combustion chamber is 3%, total pressure loss in tailpipe is 2%. One more information, it is given percentage air bleeding. it says 10% of air is taken out at 1.3 pressure ratio from HPC inlet. So, just try to understand what is the meaning of that, okay, because this is very important. Now, let us look at what next we have is the calorific value of the fuel is 42,800 kilojoule per kg. Engine mass flow rate is 550 kg per second. Consider the isentropic efficiencies of this component to be 98% for diffuser, 87% for compressor, 92% for the turbine. For fan it is 88%, burner efficiency you can say 98% and efficiency of the nozzle to be 95%. Consider say mechanical efficiency is 99%. Assume your value for Cp as 1005 joule per kg Kelvin and gamma equal to 1.4. Consider say Cp for hot gas as say 1200 joule per kg Kelvin. Consider gamma to be 1.3. We need to estimate the velocities from the core and fan nozzle. We need to calculate what will be the thrust specific fuel consumption, thermal efficiency, propulsive efficiency and overall efficiency for this engine. Let me give you the hint how do we proceed with. Just try to solve this numerical at your own and we will check with the solution in next lecture. So, component what we have is intake. For this intake the information given is flying Mach number, diffuser efficiency, entry pressure and entry temperature. So, based on that we can calculate what will be our velocity, we can calculate what will be the pressure and temperature from this intake. Next we have as our fan, that fan we are representing as process 2 to 3. For this fan the efficiency of the fan is given, fan pressure ratio is given. Based on that we can calculate what will be the exit pressure and exit temperature from the fan. We have next component as a IP compressor. For that IP compressor again we know efficiency, we know what is pressure ratio and based on that we can calculate what will be the pressure and temperature at the exit of IPC. Next component we have is HPC. For HPC also we know what is our efficiency, what is our pressure ratio. One more information given here is percentage bleed. Be careful in terms of writing this in your basic fundamental equation. We want to calculate what will be the exit pressure and temperature from the HP compressor. Next we have is our combustion chamber and for this combustion chamber total pressure loss is given, turbine entry temperature is given, calorific value of the fuel is given, efficiency of the combustion chamber is given. So, we can calculate what will be the fuel air ratio and exit pressure from the combustion chamber. We have our component as a HP turbine. For this HP turbine the efficiency is given, turbine entry temperature it is given. So, we can calculate what will be the exit pressure and exit temperature from the HPT. We have our intermediate pressure turbine. So, for that efficiency is given to us, we can calculate what will be our exit pressure and temperature from the IPT. We have our LP turbine, for that also efficiency value is given, we can calculate what will be the exit pressure and temperature from the LP turbine. We have our tailpipe information, it says there is a drop of pressure. So, that is what will give us the information about what will be the exit pressure and temperature from the tailpipe. We have our component that is turbine nozzle. For this turbine nozzle the nozzle efficiency is given and based on that we will be calculating the critical pressure. We will be comparing that critical pressure with the atmospheric pressure and based on that we will try to calculate static pressure, static temperature and exit velocity. Similarly, for the fan also based on the efficiency term we will try to calculate what will be the exit pressure and exit temperature. Once we have all this information we will try to calculate the performance parameters for this cycle. So, I am sure based on the information available with us and what cycle analysis we have done, that is what will give you idea how to solve this numerical. So, we will be discussing the solution for this numerical in the next lecture. So, here we are stopping with. Be careful with what all information that is given, what is the meaning of that, and what all we are talking in terms of numbers. Again you just go with week 2, where we have discussed from where these numbers are coming. So, thank you very much.